In this video, we will describe what is called diffraction. Some people define diffraction as the effect that waves bend around obstacles. Some other people define diffraction as interference with more than two sources. Right? Both of those are correct, and we will review examples of this in this video. I'm going to start with water waves. And instead of doing experiments in the lab to show you diffraction effects, you can actually observe this yourself using Google Earth. Right? So this is a picture of Alexandria in Egypt, and you can see an opening, and the water waves coming out of this opening have this circular propagation front. So instead of going straight, the waves seem to bend around the obstacle and propagate in all directions after the opening. This picture is from La Grande Motte in France, and you can see a protection barrier, and the waves also seem to bend around this barrier to propagate behind the barrier. This one is from Italy, and again you can see the circular erosion of the beach after the openings. You also know that sound waves do the same thing, in fact, because you can hear someone even if they are not in your field of view. Right? And you can hear them better if the door is open. So sound waves seem to go through the door and bend over towards you after they've passed the door so that you can hear the sound waves. One useful picture to understand this is called Huygens' principle. Christian Huygens was a Dutch scientist in the 1600s. And he came up with this idea. Right? If we can consider every point of a wavefront as a source of secondary wavelets, and these wavelets spread out in all directions, and the position of the wavefront at a later time is the envelope of the secondary wavelets at that time. Let me repeat this example, this principle with a picture. So we can consider every point of a wavefront as a source of secondary wavelets, so that you can see here all of those wavelets in the picture, and these wavelets spread out in all directions. And the position of the wavefront at a later time is given by the envelope of the secondary wavelets at that time. Right? And so you can see that if we have an infinite number of sources of wavelets, then we get a wavefront that seems to propagate in just one direction, even if all the wavelets individually, they emit in all the directions. And this is useful because now if you imagine a barrier, then the wavelets that are near this barrier still emit in all the directions, but now we see that the wavefront is bending around this barrier. So the waves are able to propagate behind this barrier. This principle of Huygens is a useful picture, but it's not exactly real because in reality, light does not really emit other light. Right? So, but it is still a useful idea to explain what is going on with diffraction and with other wave phenomena. When talking about diffraction, you may also encounter the term Fresnel diffraction and Fraunhofer diffraction. These two names refer to the conditions of whether you observe the diffraction far from the opening or close to the opening. In the case where you observe the diffraction relatively close to the opening, then we call this Fresnel diffraction or Fresnel conditions. And in the case where the diffraction is observed far from the opening, we call this Fraunhofer diffraction or Fraunhofer conditions. The main difference is that in the case of Fraunhofer diffraction, you can consider that all the rays are parallel to each other because the screen or the observer is far away. And if the screen is not very far, like in the case of Fresnel conditions, then you need to account for the various angles between the rays. It's not a big deal, but the Fraunhofer conditions make the mathematics a little easier. So most of the time, we will consider the Fraunhofer conditions. Right? The concepts are the same, but the calculations will be easier if we are in Fraunhofer conditions. So let's do this experiment with the laser. Right? I'm bringing a laser again, and I have this plate with various kinds of slits. And this time I will use a single horizontal slit. So with one horizontal slit, I would expect to see just one red laser spot on the board. But here is what you get. As you can see, there are several spots with bright and dark regions. The central spot is very bright, and then we have dark region and other bright spots on both sides, and so on. Now, if I use an even thinner slit, I would expect to see a thinner spot. But as you can see, in fact, if I move to a thinner slit, we can see that the diffraction pattern is even wider. So the smaller the opening, the wider the image on the board. Right? This is really counterintuitive. And we're going to explain this using what we already know about waves. Right? First, we will look at the location of the dark fringes. We will show that the dark fringes are at an angle theta, so that sine theta is equal to m lambda over a, where m is an integer number except 0. So we can write that m belongs to z star, where the star means that we exclude 0. And a in this formula is the slit width. So we start with a slit that has a width a. And let's divide this slit in a multiple of smaller strip. Right? According to Huygens' principle, each strip can be viewed as a source of waves. Then we look at the waves at an angle theta from the normal to the slit. Right? Because we assume Fraunhofer diffraction, we can assume that the rays are parallel. And so let's consider the interference from the two waves coming from two strips that are separated by a over 2. So we have already seen that the path difference between these two rays is equal to d sine theta. So here it will be a over 2 sine theta. And we also know that if the path difference is equal to half a wavelength, or 3 half wavelengths, or 5 half wavelengths, then we will have destructive interference. And so we can rewrite this as sine theta is equal to plus or minus lambda over a, or plus or minus 3 lambda over a, plus or minus 5 lambda over a, and so on. And now what we just did for these two blue rays, we can do again for the next two red rays. The two red rays have the same separation of a over 2, so the same path difference, and so they will also interfere destructively. Right? And the same for the next two, and the next two, and so on. And so they will all cancel 2 by 2. So all the rays from the slit will cancel each other, and it will be dark. And this will happen if sine theta is equal to plus or minus lambda over a, 3 lambda over a, or plus minus 5 lambda over a, and so on. And you see that we don't have exactly the formula that we want to show, because we want to show a dark fringe for any m lambda over a, where m is any integer except 0. Right? But let's consider two more cases. So let's consider these two rays that are separated by a over 4. In that case, the path difference will be a over 4 sine theta. And if the path difference is equal to, again, plus or minus lambda over 2, or 3 lambda over 2, or 5 lambda over 2, then we will have destructive interference. And this can be written as sine theta equal 2 lambda over a, 6 lambda over a, or 10 lambda over a, and so on. And again, if these two blue rays cancel each other, then the two red ones will also cancel each other, and the same for these two, and so on. And so again, they will all cancel 2 by 2, and we will have a dark fringe if sine theta is equal to plus or minus 2 lambda over a, plus or minus 6 lambda over a, plus or minus 10 lambda over a, and so on. So we have more conditions that will give you a dark fringe. But still, we don't have all the integer number. Right? We're still missing, for example, 4 lambda over a, for example. Right? But we can continue dividing this slit into more smaller sources. Right? So let's consider, again, two rays that are separated, this time by a over 8. Right? In that case, then the path difference is a over 8 sine theta, and they will produce destructive interference if the path difference is, again, plus or minus lambda over 2, 3 lambda over 2, 5 lambda over 2, and so on, which we will rewrite as sine theta is equal to plus or minus 4 lambda over a, plus or minus 12 lambda over A, plus or minus 20 lambda over A. And again, all the rays from the strips will cancel 2 by 2. And so we will have dark fringes at sine theta is equal to plus or minus 4 lambda over A, 12 lambda over A, 20 lambda over A, and so on. And so overall, what you see is that we obtain more and more of those conditions for dark fringes. And eventually, we get a dark fringe for any value of m that is an integer except 0. So let's look at what happens when m is equal to 0. M is equal to 0 means that theta is equal to 0. So it means that the rays are coming straight. And so this is the central fringe at the center of the screen. Right. So for the central fringe, the rays will interfere constructively, in fact. As you can see, the path difference between the two blue rays here will be 0. Right? They have the same length, so there is no path difference. So these two interfere constructively. But the same is true for these two red ones and these two green ones, and so on and so forth. Right? So they will all interfere constructively 2 by 2. And so we obtain a bright fringe at the center. Right? Now, before we continue, let's do an example of question. Let's imagine you have a monochromatic light of wavelength lambda that is incident on a slit of width A. On the screen, at a distance x far away, the diffraction pattern is observed, and the question is, what is the position y from the center of the pattern to of the dark fringes? So, how to start a problem like this, right? Well, always write what you already know, right? So the question is asking for the dark fringes on the screen, and we just learned that the dark fringes are given by sine theta is equal to m lambda over A, where m is any integer except 0. So you can already start by writing this. And you see that the problem is that what we want is the position on the screen, and this formula only gives you the angle theta. But we know that the position on the screen, y, is related to theta by tangent theta is equal to y over x. Right? So y is equal to x tangent theta. And then we can use the small angle approximation, and we have that tangent theta or sine theta are almost equal to theta, and so almost equal to each other. And so y is equal to x sine theta. And so it also is equal to x m lambda over A. So we've found the answer. And so you see that the first dark fringe will be at plus x lambda over A. The second one will be at plus 2x lambda over A. And there will be the same on the negative side, and so on. You see that the central bright fringe is actually twice as large as the other ones. Right? It goes from minus x lambda over A to plus x lambda over A. Now, we know where are the dark fringes, so we know where the intensity is 0, but we don't know what is the intensity at any of the other points on the screen. Right? So now what we're going to do in the remaining of this video is to look at the formula for the intensity at any angle. Right? The derivation is not very difficult. In fact, you already know enough mathematics to do it, but we're just going to skip it for this year and give you directly the formula. So the intensity for a single slit is given as I is equal to I max times the square of sine alpha over 2 divided by alpha over 2. And in this formula, alpha is equal to Ka sine theta. And so alpha, in fact, represents the phase difference between rays from the top and the bottom of the slits of width A. Now, this formula is often written with the cardinal sine function, and this function is sine x divided by x. Right? So the intensity is equal to I max cardinal sine square of alpha over 2. Now, let's discuss this formula. Right? First, let's plot it. Right? It's a rather complicated formula. You have sine theta inside another sine function, but there is one simple plot to remember. It is the intensity as a function of sine theta. If you're going to forget everything and remember only one thing, then I will recommend that you should remember this graph. Right? It is the intensity from a single slit as a function of sine theta. And you can see that it is maximum at 0. So right in front of the slit at theta equals 0 is where you have a maximum of intensity, right? So most of the light, the intensity goes straight to theta equals 0, just straight to the screen. And you can see that in the formula, you can also see that, but you need to know that the cardinal sine function at 0 is equal to 1. Right? It's not obvious because it is sine x over x. So for x equals 0, we have a division by 0, but sine x is also equal to 0, and so the limit of diffraction is equal to 1. Right? So the intensity is equal to I max. And then it decreases rapidly. Right? So most of the intensity is in fact in the central peak. And you can also see on the graph, and we have already shown that the dark fringes with 0 intensity are given by sine theta is equal to plus or minus lambda over a, plus or minus 2 lambda over a, plus or minus 3 lambda over a, and so on. And you can see that from the formula as well. The intensity will be 0 if the sine alpha over 2 is equal to 0. So when alpha over 2 is equal to plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. So we can write m pi, where m is any integer except 0. And since alpha is equal to ka sine theta, and since k is equal to 2 pi over lambda, then we have 2 pi over lambda a sine theta over 2 is equal to m pi. And you can rewrite this as sine theta is equal to m lambda over a, which is the same result we already knew before, right, for the dark fringes. Now, let's compare different types of wavelengths. For visible light waves, they range from 390 nanometers for violet color to 700 nanometers for red colors. So if you compare these wavelengths to typical objects, a typical object has the size of the order of a meter, then you see that for visible light, lambda is much, much smaller than a typical object. So lambda over a will be very, very small. And so most of the intensity, if you look at the graph with lambda over a very, very small, most of the intensity will be at theta equals 0. So that means that we only see the light that is going straight through the slit. So there is essentially no visible diffraction. But if you consider something like sound waves, remember the hearing range for humans is between 20 Hertz to 20 kilohertz. So that corresponds to wavelengths of 17 meters to 17 millimeters. Right? So that is a kind of wavelength that is comparable to the size of typical objects. Right? So in the case of sound waves, there will be diffraction around many things, right? Around your head, around your hand, around the door, and so on. And so that is why you can hear someone even if you don't see them, right? The light waves essentially go straight through the door opening, they don't diffract. But the sound waves are significantly diffracted by the door opening. And so if you consider, another example, if you consider Wi-Fi, the frequency are in the range of a few gigahertz, right? So the wavelengths are a few centimeters. It will be diffracted by many things also, right? And it can be detected everywhere, similar to sound waves. For 5G, the frequencies will be around 20 gigahertz, so the wavelengths will be smaller. And so we can put more information with larger frequencies, but you see that it will diffract less, right? So we will need a repeater to help propagate the signal everywhere. Now, let's look at this graph again. What happens if the slit is so small that it is smaller than the wavelength lambda, right? If you reduce the width of the slit A, right, then lambda over A will increase. So the central maximum will become broader. But remember that sine theta is limited between plus and minus 1. So eventually, we don't even see any dark fringes, right? Everything is part of the central maximum. If A is smaller than lambda, then there is no dark fringe, only one broad maximum. So if the width is very small, it's like the slit is a new point source that emits light in all the directions. Now, finally, I want to come back to the Young's experiment. Right? Remember that for Young's experiment, we had two slits, and we had neglected the size of the slits compared with the separation between them. And remember that we had found that the intensity was given by cosine square of delta phi over 2, where delta phi was kd sine theta. So for two slits with negligible widths, the intensity is a cosine square function. And then what we have seen today is that for a single slit, the intensity is a cardinal sine function. And so if you combine the two, that means if you take two slits, but you consider that they have a width, then the intensity will be the product of the two functions, so cosine square function and the delta of delta phi over 2 times the cardinal sine function of alpha over 2. And that is why if you look at the interference pattern from Young's experiment, you see that the intensity of the fringes decreases relatively quickly far away from the center. Right? The interference fringes are due to constructive interference between the two slits, but the intensity decreases because each slit has a small width. Right? So if you look at this pattern and you wonder, is it interference or is it diffraction? Well, in fact, it is a combination of both.